Now it's time to move into Section 3 of Chapter 9, and we're going to look at a little bit different context. So remember what we were working on in the previous section was we were dealing with proportions, and so we had a population of size of capital N, and there was a certain parameter, a certain proportion that was true for that population. And again, it could be the proportion of people who have blue eyes, the proportion of people who have brown hair, the proportion of people who are bald. So there are all kinds of characteristics that we could look at for like a human population or any type of population. And remember, we were taking simple random samples of size little n, and we were looking at sampling distributions for proportions. And when we sampled here, we were getting p hats. And so we were getting different types of sample proportions. And we found that as long as capital N was greater than or equal to 10 times little n, that we had a certain predictable standard deviation pattern. Remember that standard deviation pattern was that p times 1 minus p over n square rooted. And we also found that this distribution of these p hats would be approximately normal if we had both n times p and n times 1 minus p, as long as these were both greater than or equal to 10, the distribution of these p hats would be approximately normal, and it would center around what little p was, and we would have a standard deviation that could be judged based on this calculation. Now we're going to change gears. Now remember, we had a certain number in the population, and they had a characteristic, and we knew what proportion of the people had the characteristic. So you either had the characteristic or you didn't have the characteristic. Now we're going to change the way we look at our data. Flip the page over. And now we're going to deal with a population that, again, we can think of it as a big population, capital N being the number of people in that population. And we're still going to take samples of size n that are simple random samples, but now there's a certain mean for a numerical calculated value. It could be the length of someone's thumb. It could be the distance between your eyes, measured, say, in millimeters. It could be your height. It could be your weight. But we would actually measure some characteristic on you. And we're going to deal with distributions of sample means, meaning that, again, our original population, there's a certain size to it, but the original population has, for whatever this characteristic we're speaking about, the parameter is a mean of mu, and there is also a certain standard deviation associated with these values. So think about having 150 million people in the United States, and you've measured the length of someone's thumb. And we know what the mean of all those thumbs is, but we know that each person does not have the same thumb length, that there is a standard deviation associated with that specific characteristic. So that's the context now. We are measuring some type of a characteristic. We're not asking a question of yes or no. Now we're actually measuring a characteristic off someone. And let's look at my little simulation to talk about this idea. So assume that the height of 10-year-old males is normally distributed and that the mean is 58 inches and a standard deviation of 2.4. So again, I'm saying my whole big population has a mean of 58 inches and a standard deviation of 2.4 inches. And again, these happen to be 10-year-old boys. Now, what are we going to do? And we know the population is normal. So the actual for individual males, individual 10-year-old boys, we're saying that that distribution of height looks like this, centered at 58 inches, and has that standard deviation of 2.4. So we could add on 2.4 inches, subtract off 2.4 inches, and so we'd be here, what, at 60.4 inches, subtract off 2, that would take us to 56, and subtract off another 0.4, so that would take us to 55.6 inches, etc. So we know that this is the distribution for individual boys who are 10 years old. Okay, now, what are we going to do? We are going to take a simple random sample of 40. So I'm going to pick 40 boys. simple random sample, so we're getting unbiased data, and we're going to find an X bar. And then we're going to do it again. And we're going to do it again. And so I did that in my simulation. I did the following. I did rand normal. I have the mean of 58, the standard deviation of 2.4, and I got 40 boys randomly from this picture. I actually stored them into list 1, and then with a colon, I did mean of list 1, and that allowed me to find the mean of my 40 numbers. And I could actually go through and look at my list 1 and see how variable they are, but again, they're going to come from this distribution. Now, I did that. My first time I got a mean of 58.2. I hit the button again. I got 57.88. Again, this number came from finding the mean of 40 numbers. I did it again. I did it again. I did it actually 20 times. I said to do it 30. I got tired of doing it, as a matter of fact. And so, in any case, each of these numbers comes from grabbing 40 numbers from here and finding the mean. Now, the question is, what type of a distribution would I expect these numbers to take on? And as you might expect, if I graph a histogram of these numbers, put these all into my calculator into a list, and graph a histogram of this data, this will not necessarily be a nice bell-shaped curve because I only have 20 numbers here. But if I do this all day long, I sit here all day long and just keep hitting this button and finding the mean of 40 numbers, each of which comes from this distribution. And if I graph all of these X bars for a very large sample size of these values, I will end up having this distribution look very bell-shaped and normal. And I ended up, remember, my original distribution of individuals was centered at 58 inches. And if I found the mean of these values, I actually got the mean of the means to be very close to 58 inches. I kind of expected that. Now, the standard deviation of individual boys' heights was 2.4 inches. The standard deviation of all of these X bars that I have so far is only 0.38. So these are much less variable than what an individual boy's height is. And that's to be expected. And what happens is, if your original distribution of individuals is normal, which mine was, if I take simple random samples of size n, I will expect this new sampling distribution of X bars. I will expect that sampling distribution to also be approximately normal, and I expect the mean of my X bars to be approximately equal to what the mean of the individual heights was of the boys. Now, what do I expect the standard deviation to be? The standard deviation of the X bars is expected to be what the standard deviation of individuals is, but it's divided by the square root of n. Now again, if my original distribution is normal, and I was told that it was normal, then my sampling distribution of X bars for a given sample size n will be approximately normal, and I will have it center at the same place as where the population was centered. However, the standard deviation will be smaller. It will be smaller by a factor of the square root of n. And that's what we have as far as our information discussed at the bottom of this. That's what this is telling us in here. And if we notice back up at the top, that if I would have taken my 2.4 inches, which was what the standard deviation was of the individual boys' heights, and if I divide it by the square root of 40, which was the sample size, I get about 0.38, and lo and behold, I actually just kind of got lucky on this because normally I'm not quite that high with only a sample size of 20 different means here, each coming from 40 boys' heights. But the more data you collect, the more likely your sample data is to approach this number. Okay, now what do we do if our original population is not normal? So let's turn the page. And we have an extremely important theorem that you do need to know by name, and that is the central limit theorem. And the central limit theorem basically tells us this. If we have a population, I'll call that there are capital N numbers in this, so that's the population size, and there is a certain mean and there is a certain standard deviation associated with it. These are individual people in here. And again, you're not saying yes, no to someone, do you have attached earlobes or not? Did you make a basket or not? That's not the context of this. You had to actually measure a characteristic off a person for this, or you had to measure the weight of a penny. You had to measure the length of a plant. You had to take a measurement off the person. And so the individuals have a certain population mean, and they have a certain population standard deviation associated with it. And now, we don't know what the distribution shape is. It can be non-normal, and this is the beauty of the central limit theorem. If you take large, and I'm going to put that in quotes, sample sizes, and they're simple random samples, this distribution, as you let this sample size become larger and larger, this distribution will have a mean for x bars to be approximately equal to the mean of the individuals, and the standard deviation of x bars for a sampling distribution will be approximately equal to the standard deviation of the individuals divided by the square root of n, and it will be approximately normal as you let this sample size get bigger and bigger. Now, if I have a very non-normal distribution to begin with, say I have something that is really, really skewed off to the right, and if I sample small samples and I get a couple numbers, say I get 2 numbers from here and I find an x bar, and I take 2 numbers from here and I find another x bar. If I take 2 numbers from here and I find another x bar, if I graph these and the sample size is only 2 and the original distribution was skewed, I don't expect these numbers to form a normal distribution because I don't have a very big sample size. This distribution would still be skewed to the right. Now, it wouldn't be as skewed as this one, but it would still have a distribution that would be skewed to the right. Now, on the other hand, let's say I take 20 numbers from this population. I take 20 numbers and get an x bar, 20 numbers and get an x bar, 20 numbers and get an x bar, and again, do this over and over again and graph these values. These values will be closer to a normal distribution than the sample size of 2. There isn't a general rule in reality for how big does this sample size need to be in order for these x bars or the sampling distribution of x bars to be approximately normal. But normally a textbook will say if you want to come up with a number just kind of as a good number to base it off, once you get to a sample size of about 30, most distributions, sampling distributions, will tend to have the normal characteristics turn up if each of these x bars is coming from a simple random sample of about 30. And again, the more oddball this original distribution is, the larger this sample size to be. If this distribution is not normal, but not terribly off from being normal, then you might actually have these x bars have an approximate normal distribution with a smaller sample size. If this has, a graph that looks like this that really looks kind of weird shaped, then maybe you need a little bit bigger sample size for this. But in general, if you had a sample size of 30 or higher, most distributions will have the x bar sampling distribution look approximately normal. So the cool thing is I can start with a distribution that's non-normal, and if I sample a large enough sample size, I will produce a sampling distribution that will be approximately normal. So let's see, how do we use this information? So let's say we have the scores of students, and I'm trying to get a piece of paper that's blank. There we go, that looks close enough. So we have the scores of the students on the ACT for a certain year, a recent year. Let's say that were approximately normal. We know they can't be perfectly normal because the scores on an ACT are individual integer points, and the normal distribution will assume that they're on a continuum. But this distribution is approximately normal, and let's say it's centered at 18.6 and a standard deviation of 5.9. Now these are for individual students, what the score information is. So I said draw a picture. Because I've said that the distribution is approximately normal, we can draw a picture like so, where we know that if we go out one standard deviation, we expect 68% of people to have scores in here. If we go out 2 standard deviations, we expect 95% in here. And if we go out 3 standard deviations, we're going to have 99.7% of people score between those values. And again, we know that individual scores really are integer scores. Now, we can answer questions about this. Because it's in a normal distribution, or at least approximately so, what is the probability that you randomly choose a single student and the person has a score that is 21 or higher? Well, I can look where 21 is here and higher. And because of the normality of the distribution, I can find what that area is or what the probability is. Convert it to a z-value. My z-score is about at 0.4, higher than the mean, and find the corresponding probability. But now here's a more interesting question. Now we're going to take a simple random sample of 50 students, and then we're going to find the x bar of those 50 students. So here's the individual distribution. We're going to get 1 person, 2 people, 3 people, 4 people. We're going to randomly get 50 people from this distribution and then find the x bar of those 50 people. And we want to know now, what is the probability that this mean score of these 50 students is 21 or higher? And we have a different distribution. We know that if you continue to take from the original distribution 50 numbers, find the mean, get another 50 numbers and find the mean, get another 50 numbers and find the mean, that the mean of those x bars will center the same place as the individuals. However, here's the first x bar. Here's the second x bar. Here's the third x bar. These x bars are not going to all be 18.6. They're going to vary. But remember, each of these comes from 50 numbers that were averaged together. These will have a variability of the standard deviation of individuals over the square root of n, only 0.83. These are not going to vary like individual test scores will vary. And so the original distribution was normal, so this will automatically be normal. Now I have a fairly big sample size here of 50, and remember I said you're usually pretty safe if your sample size is 30 or higher. So 50 is a pretty large sample size when we're testing with means. But regardless of this sample size, this distribution was going to be approximately normal since the individual distribution was normal. So I drew a picture of my sampling distribution. Now again, this is not for individuals. This is the sampling distribution. So the sampling distribution of x bars. And each of those x bars is coming from a mean of 50 numbers. And this is the variability I expect for the x bars, each coming from a size 50 sample. And so now I can find the likelihood of having an x bar being greater than or equal to 21. And I convert it to a z-value, just like normal, but look at how I have a different calculation down here because I have to use the standard deviation of x bars, not the standard deviation for individuals. And now I can see my z-value is significantly higher. It's almost to a 3. And my area above that is 0.002. So if the actual population mean is 18.6 and you take a sample of 50 numbers from here and find the mean of those 50 numbers, it's extremely unlikely that you're going to get the mean of those 50 numbers being 21 or higher. It happens less than about a fifth of a percent of the time. Now, the law of large numbers we talked about once before, and let me just bring it up again, that The idea is, as we remember, as we draw more and more samples, the more likely you are to obtain the actual population mean when you draw more and more samples. So if we draw observations at random from a population that has a mean mu, the number of observations increases, we expect the X bar to get closer and closer to the mean. So if I take even larger sample sizes than 50, then I'm going to have less variability between my X bars, and there will be much closer to this 18.6, although this standard deviation is still relatively small. But I keep cutting down the variability of my X bars as I increase the sample size. So now it's time for you to practice in class.